we will see the generation techniques of double sideband suppressor carrier waves. So as said, DSP wave simply consists the product of message signal and carrier signal. A device for achieving this requirement is called a product modulator. Since it is the product of message signal and carrier wave, we can use a device which is known as product modulator. And we have two forms of product modulator, namely balance modulator and ring modulator. This diagram shows the balance modulator. So a balanced modulator consists of two standard AM modulators arranged in a balanced configuration so as to suppress the carrier wave. So it will have two AM modulators, that is standard AM modulators. And we assume that the two modulators are identical except for the sign reversal of the modulating wave applied at the input. So these two AM modulators are identical. Both the modulators will be having same characteristics, but the only difference we get is that the sign of the message signal applied to these modulators. So if we observe this AM modulator one, so here the input is m of t, but for the second AM modulator we have the input as minus of m of t. So for one modulator we are directly giving the message signal, and for the other AM modulator we are giving minus m of t. And we have an oscillator which will generate the carrier wave. So a single oscillator is used to generate the carrier wave, and this carrier is given as input to both the standard AM modulators. So for the first AM modulator, the two inputs will be m of t and c of t, and for the second AM modulator, the inputs will be minus m of t and c of t. So the outputs of this standard AM modulators are given to the summer. So here this if S1 of t is the output of this modulator, and S2 of t is the output of this second modulator. So the final modulator signal will be S1 of t minus S2 of t. So this S2 of t will be subtracted from S1 of t, and we will get the final output. So this is how the balanced modulator works. So it will basically use two standard AM modulators, and by using these two, it will generate the DSBSC wave. Since these are standard AM modulators, the output of these two modulators can be expressed as. So we know that the output of the standard AM wave is AC into 1 plus Ka m of t cos 2 pi fct. So S1 of t will be AC into 1 plus Ka m of t cos 2 pi fct. And for the second AM modulator, so S2 of t will be AC into 1 minus Ka m of t. Since here we are giving minus m of t as the input, so here the modulator signal becomes AC into 1 minus Ka m of t into cos 2 pi fct. So simply we are replacing this m of t by minus m of t for second AM modulator. So now if we subtract this S2 of t from S1 of t, so we'll get S of t will be S2 of t minus S1 of t. So if we subtract S2 of t from this, so this AC will be cancelled out, and Ka m of t minus of minus Ka m of t will become 2 Ka AC into cos 2 pi fct into m of t. So if we subtract these two signals, we will get 2 Ka AC into cos 2 pi fct into m of t. So we can obtain the product of the carrier signal and message signal. So this part is the carrier signal, and this is the message signal. But we have a scaling factor of 2 into Ka. So hence, except for the scaling factor 2 Ka, the balanced modulator output is equal to the product of carrier and message signal. So this is the since the product of this message signal and carrier is the DSBSC wave. So by using this balanced modulator, the DSBSC wave can be generated with a scaling factor of 2 into Ka. So this is how we can use two standard AM modulators in order to generate the DSBSC way. Now we'll see how ring modulator can be used to generate DSBSC way. So one of the most useful product modulators that is well suited for generating a double sideband suppressor carrier modulated wave is the ring modulator. And it is also known as lattice or double balancing modulator. So this is the circuit for ring modulator. So it consists of 4 diodes and 2 transformers which are center tapped. So the 4 diodes form a ring in which they all point in the same way. So these 4 diodes are arranged like this in the form of a ring. And here the diodes are controlled by a square wave carrier of frequency Fc, which is applied by means of 2 center tapped transformers. So we have 2 center tapped transformers and carrier wave is applied at these taps. Based on the carrier voltage, these diodes will be either forward bias or reverse bias. And we assume that the diodes are ideal and the transformers are perfectly balanced. So we assume that these diodes have ideal characteristics. So here we will be giving message signal as input. And here we will be giving carrier at the center tap. This will be carrier. And this will be the modulator signal, that is DSBSC way. So now, so the diodes are arranged in this form, that is they will form a ring like this. So let us name these diodes as A, this one B, this one C, and this one is D. So now let's say that carrier applied is positive. So if we are applying, if the carrier voltage is positive, so what will happen is here it will be positive and here it will be negative. Since we are applying, since the carrier, when the carrier is having positive voltage or positive half cycle, so here the positive sign will come and here it will be negative. So if you see the signs across this diode, so P side it will be, here it will be plus, it will be minus, here it will be plus, here it will be minus. So for this diode, it will be plus here, it will be minus here, and here it will be plus, and here it will be minus. So if you observe these 4 diodes, so this for diode A, P side we are supplying positive voltage and N side it is negative. So this diode will be switched on. Similarly, diode B also. So at the P side we are applying positive voltage and at the N side we are applying negative voltage. So this diode will also be on. And coming to the diode C, if we see that positive voltage is applied at the N side of the diode and negative voltage is applied at the P side of the diode. So this diode will be off. Similarly, the diode D, here also you can see that positive voltage is applied to the N side of the diode and negative voltage is applied to the P side of the diode. So C and D will be off. And since we are treating these diodes as ideal, so now the circuit becomes so here diode A is short circuited since it is on and we are treating them as ideal diodes. So the circuit will look something like this. So this is diode A. So this one will be short circuited. Similarly, diode B will also be short circuited. And these 2 diodes C and D will be open circuited because they are switched off. And since these diodes are ideal, so diodes will be open circuited. So here we are applying M of t, and here the carrier is applied over here. So now, since we are using ideal transformers, so the same M of t will be applied over here, will appear over here, and here this S of t will be same as input. That is, S of t will be equal to plus M of t. So in a transformer, we know that the input voltage will be appeared over here. So since this is short circuited directly, so the same M of t will be appearing over here. And again, the same S of t will be equal to M of t. So this is when carrier is positive. And let's see the second case. So if the carrier is negative, so if carrier is negative, what will happen is, so now if the carrier is negative, so here it will be negative voltage, and here it will be positive voltage. So if we draw this over all the diodes, so it will be negative, it will be positive. The same negative voltage will be appearing over here, and here it is positive. Similarly, same, it is negative and it is positive. So now if we see it clearly, so for the diode A, at the P side we are applying negative voltage, and at the N side we are applying positive voltage. So this diode A will be switched off. Similarly, the diode B also. So since we are applying negative voltage on the P side and positive voltage on the N side, so this diode B will also be switched off. And if we see the diode C and D, so negative voltage has been applied to the N side and positive voltage has been applied to the P side. For diode D also, you can see positive voltage at the P side and negative voltage at the N side. So these diodes C and D will be switched on. So when the carrier is negative, the exact opposite condition will occur. So diodes A and B will be switched off and C and D will be switched on. So now if we see the circuit, so it will look something like this. So here diode A, so here we can see that the diode A and B are switched off, and these diodes are switched on. That means they will be short circuited. So this is M of t. So here, if M of t is applied over here now, so here you will get plus M of, here it will be plus, it will be minus M of t. So now since the diodes C and D are switched on, you can see that this minus will appear over here because it is connected from here. So this will be minus and this will be plus. So it will be minus M of t over here. So now the final signal will be S of t is equal to minus M of t. So here in this case, since the A and B are short circuited, so the plus and minus will be appeared directly when carrier is positive. But when the carrier is negative, since these diodes C and D are short circuited, so here instead of M of t, minus M of t will be appearing, and hence the output will be minus M of t. So when the carrier is positive, S of t will be plus M of t, and when the carrier is negative, S of t will be minus m of t. So the same thing has been shown in the slides. So when carrier supply is positive, the outer diodes are switched on. That means the diode A and B are switched on. And since they are ideal, they will be presenting zero impedance and hence they will be short circuited. And the inner diodes C and D are switched off and they will be open circuited. So the modulator multiplies the message signal by +1. Since the same voltage has been applied, the output voltage will be equal to m of t. But on the other hand, when the carrier supply is negative, the situation will become reversed and the modulator multiplies the message signal by -1. So if we see when carrier is negative, so this part, this diode and this diode will be switched off and these two diodes will be switched on. So here you can see that the sign has been reversed and hence the message signal will be multiplied by -1. So hence we can treat this ring modulator as a product modulator for a square wave carrier and the message signal. So since when the carrier is positive, it is being multiplied by 1, and when the carrier is negative, it is being multiplied by -1. So we can treat this as product of message signal and square wave carrier. So here, that is what has been shown here. So this is the modulating wave, m of t, that is message signal, and square wave carrier. So ring modulator output can be treated as multiplication of this message signal with square wave carrier. So now again, by using Fourier series expansion, as we have seen earlier in switching modulator. So if we find the Fourier series representation of the square wave carrier, so we get this. It can be expressed as C of t is equal to 4 by pi sigma n equal to 1 minus power minus 1 power n minus 1 by 2n minus 1 into cos 2 pi fct into 2n minus 1. Since this is a periodic signal, so we need to calculate an, a0, an and bn, and by using Fourier series expansion we can get this expression. Since C of t is this one, so the ring modulator output is therefore the C of t multiplied by message signal m of t. So as we discussed, this is basically a product modulator. That means the product of message signal and carrier signal. So once we multiply this message signal with this carrier, so this is what the modulated wave looks like. So since here the message signal has been crossing the zero axis here, so there will be phase reversals. So since there is a sudden change in message signal from positive to negative, so at this zero crossing points, there will be phase reversal. So as we have seen this earlier, so this is how the DSBSC wave looks like. By using this, we can obtain the product of carrier and message signal, which is nothing but DSBSC wave. So here we can see that there is no output from modulator at carrier frequency. So here we can see that there is only the product of message signal and carrier signal, and there is no separate carrier component as in standard AM wave. So if you see the standard AM wave, it is having separate carrier component plus product of message signal and carrier signal. So since in DSBSC, we do not transmit the carrier, that means we are suppressing or removing the carrier component. We should have only the product of message signal and carrier signal, and this separate carrier component should be removed. So if we see this expression of the ring modulator output, we can see the product of cos, that is carrier signal with message signal, and we do not have any separate carrier component. So we can see that there is no output from the modulator at carrier frequency. We don't have any component at carrier frequency, but only we have the components at the product of the carrier and message signal. So this is how a ring modulator can be used to generate the DSBSC wave.